Hey guys, this is notes number 11, titled Disk and Washer Method. Go ahead and write down your FLT here. Press play whenever you're ready. Okay, so given functions or singular of function, you're going to be able to visualize and calculate the volume of what we call the solids of revolution, okay? Using two methods that you're going to pick up today. It's called the disk and the washer method. So just to kind of recap, you started this unit approximating the area under the curve by drawing a bunch of rectangles, right? Or trapezoids. And then you learned that if I increase the number of rectangles or the number of trapezoids to an infinite amount, you'll end up getting closer and closer to the true area under the curve, which we learned to be integrals. So integrals help you find the true area under the curve. So now how can we take that a step further, right? How can we actually find some volumes? So this right here, you're able to create three-dimensional shapes, shapes that aren't always so clean, so rigid, some that you may have seen in geometry or integrated math 2 or 3. But basically, this is what you want to pick up: the disk method and the washer method, okay? What it is and how it works in a second. But you want to make sure that you have your graphing calculator ready to go. Make sure that you reset it, second plus 712. And I'll show you guys how to do the math by hand, and then also how do we use it on a calculator as well, okay? But it shouldn't be that brand new because you're still integrating, so it does refresh what you guys have been learning in the last few lessons, okay? All right, so here's a recap, and you don't have to write this down. You guys had a function, right? And we tried to find the area under the curve, or even multiple curves, from one moment to another. And before you found the area under the curve, we approximated, okay? And we drew a bunch of rectangles, right? But let's just focus on one of them, right? This right here, keep in mind, is a vertical rectangle. So you know that the width is delta x, right? So you know that this is going to be some version of dx when you want to integrate, okay? Because it's a vertical rectangle, so that doesn't change. But what would happen if I were to revolve this rectangle, if I were to spin it, in a sense, across this x-axis right here? If you were to spin it constantly, what solid of revolution would that make? Okay, think about it. If I were to spin this, what would it make here, right? So here's a little visual about that. So you got this rectangle here. We're spinning it. And what's happening is you're creating what we call a disk. It's like a really short cylinder. If you were to lay it flat, it would kind of look like a one-layered cake, right? It lays flat. Notice how this is a three-dimensional shape now. So when you get into 3D, you start talking about things like volume, okay? So this is just one rectangle, okay? Now, what if we were to focus on all the other different rectangles? And what if we were to rotate all of these all at the same time, right? What kind of picture would we get there? So here's another visual so that you guys can get an understanding of it. Where is it? Okay, so for instance, here we have this blue area under the curve. If you were to just focus on this one rectangle here, if you were to spin it, it would create this disk, okay? Three-dimensional, completely solid, right? But if we were to think about all the other rectangles that are nearby it, right, what would it look like? It would kind of look like this, okay? And if you look at it sideways, it's kind of like a multi-layered cake, right? But notice how it's a little bit bumpy, right? It doesn't give us the exact smoothness of this blue curve here, right? So that's where the integration comes in. When you integrate, you're squeezing in an infinite amount of rectangles, which in turn squeezes in an infinite amount of disks. So then you end up getting something smooth like this here. It kind of looks like a Hershey's Kiss of some sort. All right, if you look at it sideways. So that's the disk method, right? So how does it work? First off, here are some solids of revolution. If you notice, there's always some type of line of symmetry where if you were to spin it, you would create the solid of revolution. Okay, kind of like this piston right here, or this bottle, or this pill. It was all created by some function that you revolve around a certain axis. Okay, so this is actually how deep into the coding of 3D printing works. When you want to 3D print objects, specifically with solids of revolution like this, you can input a lot of the coding here with calculus. Okay, so here we go. So if you think about that one slice, just one slice, and I were to lay it down, okay, this is a really short cylinder. So just to give you a little bit of a refresher with geometry or integrated math 2, a cylinder is kind of like a prism, but they don't call it a prism because it's not rigid. If you guys recall, to find the volume of a box or a prism, it's really just the area of your base times your height, which is really just length times width times height for this prism here. But for this disk, it's really the area of your base. Your base is a circle. So to find the area of your circle, it's really pi r squared times the height. Okay? So your height is right here. So if you think about it, if I were to turn that, and hopefully, actually, you know what? Let me try this. If I were to duplicate it and then turn it sideways, notice how that height is really your delta x here. Okay? Your height is really your delta x. Okay? So if you think about it, what I'm doing here to find the volume of all of these cylinders all at the same time, we can integrate to keep it faster. This is pi radius squared. And instead of h, I'm going to put dx because that's really our delta x right here. And this is where we get this formula. All right? So go ahead and write this down. It depends on where your axis of revolution is. If it's a horizontal axis of revolution, you'll have that with respect to x. Vertical axis of revolution is with respect to y. But I'll show you a picture so you get a better idea of how to actually use it, okay? Okay, so here's the same thing but with a picture. Here's what I want you guys to keep in mind. If we had a horizontal axis of revolution, meaning we're spinning this in a horizontal motion, right? Notice how your rectangle is vertical, okay? And notice how when you have a vertical axis of revolution, our rectangle is horizontal here. And remember, horizontal rectangles give you a dy, right? Vertical rectangles give you a dx. And I would encourage you to write down these pictures, okay? Or draw out these pictures. Okay, so my question to you guys is, what do you guys notice about the direction of the axis and the rectangle? How are they related, right? Okay, so if you notice here, they create like that T shape. In geometry, there's a word for that when they kind of create that perfect T shape. It's called perpendicular, okay? So an easy way to remember this, especially when you're learning all these different methods, is we can say that these are, and write this down and highlight it, these are really perpendicular. okay? Very silly, but it will stick with you guys, okay? It's very helpful in terms of which method you should use. But just remember this phrase. This method is always perpendicular. Your axis of revolution always has to be perpendicular to your rectangle. Okay? So let's try it out. Here we go. Write this one out in its entirety, and then press play when you're ready. We'll call this example 1. Okay, so taking a look at this function here, I think you guys would agree that this is not something that they would expect you to graph by hand. Okay, so go ahead on your calculator, y equals the square root of sine x. Okay. Okay, and notice here how it says that you're going from 0 to pi, right? So what you want to do here is go ahead and go to your window, which is that second button at the top. I would probably change that to 0, and your x max, I would probably change that to pi. So you know exactly which one you're dealing with here, okay? In case you can't find that pi button, it's right above the caret. So second caret would give you pi. Once you hit graph, it kind of looks like this, but I'm going to go ahead and dilate it a little bit. It kind of looks like this some way or another. On your graphing calculator, it's probably looking like this, but I want to make sure that I have enough room to draw in between, okay? So here's what we know. We went from 0 all the way to pi. We have this region. Okay? So first step, draw your picture. Second step, indicate where you're rotating this. And the way you figure that out is you look for a word. Let's use this one, about. Okay? That tells you where they're going to rotate. So here, we're rotating this volume or this solid about the x-axis. So the x-axis is horizontal. So I'm going to go ahead and draw kind of a looping motion there to indicate that that's where I'm rotating. So notice how where I'm rotating or revolving is horizontal. So my rectangle should be vertical. So you draw a sample one anywhere inside your region. Okay. I know it has to be vertical because it has to be perpendicular. Okay. So once again, the axis of revolution was horizontal, so I want this to be perpendicular to that. And you guys remember that whenever it's a vertical rectangle, that means it's dx. So that's the purpose of drawing it out, okay? So we have dx here. Volume equals, I know it's going to be the integral with the pi on the outside of some radius squared, okay? So I know the region starts and stops from 0 to pi, so I'll put that in there. Now the radius is this right here. That's how tall your function is. So going from the x-axis all the way up, that's really just your function, okay? And notice how the height changes, right? So if you input your function, it will follow according to wherever you are on the x-axis, okay? So you're just going to put in whatever f of x is. In this case, it's the square root of sine x. All right? Okay. That's pretty much it. All right? Here, you could actually simplify it. The square root and the square cancels out. You're left with the integral of sine. Okay? Try to do this by hand, just this problem here. Press play when you're ready. Okay, so here the integral of sine is negative cosine, so that's negative pi cosine of x from 0 to pi. So that's the same thing as, I'm going to go ahead and factor out the negative pi. That's cosine of the upper minus cosine of the lower. Okay, so this I'll be left with negative pi times the cosine of pi is negative 1. Cosine of 0 is 1. So this looks like it comes out to, I want to say 2 pi. Okay? What does that represent? If you were to make this three-dimensional shape, this is how much material you would need to create this solid. So this is specifically beneficial for manufacturers, right? When you're trying to figure out, well, how much is it going to cost to create products from 3D printing, right? And can you guys imagine, here's a question, can you guys imagine what the shape would be if we were to spin this? Okay. Now, by visualize in the FLT, I'm asking you guys being able to draw out this graph here. Trying to visualize the 3D picture isn't really necessary, but it's always nice to know. But this is actually what it would make. It kind of makes like a footballish shape or like a Stewie head, right? But that's it. All right, let's try a couple more. Let's try this one, part B. Okay, what I want you to write down, let's shorthand this one here. We want to rotate about the x-axis under the curve of y equals square root of x from 0 to 1. Just write out what I'm highlighting there so we can shorthand it. Okay, here we go. First step, you always want to draw a picture. That's the first place you want to go to, okay? This is definitely a non-calculator question. You should be able to graph the square root of x by hand, but if you forgot, this is why we're refreshing, okay? So here we go. So we draw our x and y axis. We know that the square root of x is just a half of a sideways parabola. I call it a hook, but it looks something like this. And we're going to go from 0 to 1. So from 0 all the way to 1 there, okay? So we have this nice region here. Okay. Remember, what else do you want to indicate? You want to indicate where we're rotating this, okay? We're rotating this about the x-axis, so I'm going to go ahead and put a loop here. You can even put it over here, really doesn't matter, but I tend to try to push it towards the right, wherever there's space. Okay, so you don't need to highlight this part. It's really just to show you guys. We have a horizontal axis of revolution, so that implies that we should have a vertical rectangle. Okay, so I'm going to draw a sample vertical rectangle. We know it's vertical because it has to be perpendicular. Okay, it's silly, but it'll click with you guys. All right, here we go. That vertical rectangle tells me that I will integrate with dx. Perfect. Here we go. V equals pi integral of something dx, right? I know that I'm going to go from 0 to 1 because that's where the region starts and stops. Okay? Pi radius squared. The radius is determined by this height right here, which is our function, happens to be the square root of x. All right? Because when you're going from the x-axis up, it's always going to be the function, right? And then you just chug, right? Either through a calculator or by hand. This one's easy enough to do by hand. Here we go. This is just pi integral from 0 to 1 of x dx, because the square and the square root cancels out. And then we're going to be left with pi x squared over 2 from 0 to 1. And that's equal to pi times 1 squared over 2 minus 0 squared over 2. And if you plug and chug enough, that'll come out to pi over 2, which is the volume, okay? How much material you need to build that shape, all right? Can you guys imagine what that three-dimensional shape would look like if you were to spin this shark finish shape? Shark finish shape. That's tough to say. Okay. It would kind of look like what I describe as like a sideways cone head or like a bullet. right? Kind of looks like that. But again, doesn't matter as long as you know how to calculate it, right? Okay, here's another one. Part C. Go ahead and write down those three equations about the y-axis. Go ahead and write that down. Okay, first step is the graph. Here we go. You should be able to sketch this by hand. If you don't remember how cubics look, it's okay. That's why we're refreshing. Okay, y equals x cubed looks a little bit like this. Okay, y equals 8 is a horizontal line. And x equals 0 is really just your y-axis. That's x equals 0, a vertical line. Okay, so I noticed that there's a shaded region right here. All right. What else do we include? Okay, where are we revolving this or rotating this? We're rotating this about the y-axis this time, right? The y-axis. So we actually have a vertical axis of revolution. So that would mean that we should have what type of rectangle? Press play whenever you're ready. Since the axis of revolution is vertical, the rectangle should be horizontal because they have to be perpendicular. Okay? What does this tell me? Horizontal rectangles tell me that we're going to integrate with dy. That means everything here has to be with respect to y, okay? So I'll write it right here. V equals pi integral of something squared dy. Okay? So notice that from here to that green function, okay, that is the height of the horizontal rectangle. And it hits that function y equals x cubed. This right here is y equals x cubed. But since everything has to be with respect to y, we have to find the equation in terms of y. So y equals x cubed, if you were to solve for it, I would cube root both sides. X would equal the cube root of y, also known as y to the 1/3 power. Okay? So I'm going to go ahead and write that in there. You would not put an x cubed because you're integrating with y. Okay? So just like the function had to be in y, the bounds also have to be in y. The region starts down here and it goes all the way up to here. So it starts from the y value of 0 and it ends to a value of 8. Okay? So pay attention to your axis of revolution, okay? It does change the way that you set up your equation. All right, solving it is the same way. V equals pi. So remember, if you have power of powers right here, you could just multiply them. So that's really just the integral of y to the 2/3 dy from 0 to 8. Let me squeeze in another page here so you can see. Okay, so that's really just pi of what, right? Go ahead and pause here and actually try this on your own. Okay, so here, this is just going to be y to the 2/3 plus 1, which is y to the 5/3 over 5/3 from 0 to 8. All right. Dividing by 5/3 is the same thing as multiplying by 3/5. I could take that coefficient outside to make it a little bit easier. And then I'll go ahead and evaluate from 0 to 8 using the fundamental theorem of calculus, okay? Here we go. 3/5 pi times 8 to the 5/3 minus 0 to the 5/3. Okay? That's really it. I'm going to go a little bit further, but don't let that kind of overshadow the importance of the problem, okay? 0 to any power is 0. That's easy to remember, okay? So here, what you have to do is you have to raise 8 to the 5th power, but then you also have to take the cube root. okay? Or you could take the cube root and then raise it to the 5th power. I always like to cube root first because it makes the number smaller. The cube root of 8 is 2 because 2 times 2 times 2 gives you 8. So the cube root of 8 is 2, and 2 to the 5th power is 32. 2, 4, 8, 6, yes, 32. And then whatever that comes out to, right? 96 pi over 5, which is how much material you need to build this object. All right. Whoops. And that kind of looks like a bullet shape too, right? Okay, so notice how this problem was a little bit different because of where you're rotating. Because this had a vertical axis of revolution, your rectangles were horizontal, so your integration was in terms of y here, all right? When you have a horizontal axis of revolution like this one, your rectangles were vertical. Remember, they have to be perpendicular. It's a very important term that I want you guys to remember, okay? Okay, here we go. Let's try another one. Oh, okay. So here's the next one. And I'll show you through a simulation here. Actually, I'll show you two. I'm only showing you this one because it's just, I nerded out and it looks super cool. So hopefully I don't screw this up here. I probably will, but who cares? Okay, so here you see this red parabola upside down. And then you have these two orange bars, which is where we're going to start and stop, okay? What we're going to do here is we're going to go ahead and create rectangles, right? So what's happening here, from what you can see so far, is we're creating, I believe, 5 sub-intervals, okay? And I'm going to pause here for a second to find the area under the curve, right? And then you guys learned that if I squeeze in more rectangles, I will get the true area under the curve. But on top of that, if I were to spin these rectangles in a circular motion, I get a 3D solid of revolution. So it's kind of cool because, take a look here, I can go ahead and change the perspective, kind of tilted sideways here. So what we're doing is we're wrapping this up in a circle. And right now we still only have 5 discs, but take a look at what happens if I were to increase the number of sub-intervals or subdivisions, okay? You notice that the solid starts to fill up. You guys see that? It's pretty cool. It starts to fill up, right? So that when I keep rotating this, if I can move, whoops. Let me pause that for a second. If I rotate this, you'll see that they're kind of at a current Pac-Man shape, right? But you're slowly wrapping it all at once. So you have like millions and millions of discs that are super thin, like CDs, and you're wrapping it all the way through, creating these discs, okay? And you're adding it all up at the same time. And I'm only doing this because it's just super cool because you're just rotating in every direction. But anyways, hopefully you guys are getting a picture of this. Now, if you notice in this one, if I can stop at the right moment, I cannot stop at the right moment. Sometimes, depending on your function, you won't always get a complete solid, okay? So for instance here, let's say I want to rotate this about the y-axis, okay? You're going to notice, and they'll show you this very quickly, and I'll kind of try to talk you through it. First, they cut it up into sub-intervals, okay? If you notice at the bottom rectangle, okay, it's hugging the y-axis, right? But the top rectangle right there, the purple one, when you rotate it, it's not creating a disc. There's actually a hole there. So one is hugging the y-axis, the other one isn't. So when you revolve it, one has a gap and one doesn't. right? So these four at the bottom right here are all disks because it's a complete solid, right? But as you move on to the last four, you notice that there's more of a gap here. And it gives you this picture, right? Which is not the best picture because they didn't use that many subintervals, right? But what if they were to squeeze in an infinite amount of subintervals? What would it look like? And this animation does a somewhat decent job here by rotating this around the y-axis. You'll see right here. So it wraps kind of like behind that y-axis first, and then it'll wrap in front of the y-axis. So what they're doing is they're simultaneously wrapping around an infinite amount of discs and washers all at the same time. So here's what happens. If you have a rectangle that's essentially floating, notice how it's not hugging the axis of revolution, right? There's a gap. So it only makes sense that when you revolve it, it creates a disk, but there's an obvious hole right here, right? They have a fancy name for that. They call it a washer. Not because of the washing machine, but if you guys have ever, if you've ever played with anything at IKEA, if you've ever assembled anything at IKEA, they give you these little like metallic donut shaped things. Those are called washers, and that's where they get it from, okay? So these are still three-dimensional, but there's a gap. So here's my question to you guys. What do you think happens to the formula? Okay? How do you think we adjust the formula if we want to find the volume of a washer? Okay? Really think about that because it's very logical, okay? And if you don't think of it right away, that's okay, but it will make sense to you, I hope, through this explanation that's coming up. But try to come up with it on your own. So for a disk, we know, at least when we revolve around the horizontal axis, it's V equals pi r squared dx, right? From A to B. Okay? So the only thing that makes sense is, well, let's pretend that we have a solid disk, and let's take out that tiny little solid disk, and then we'll eventually get this picture. So if I calculate the volume of the whole disk and I subtract out that tiny little disk, I should get my washer. So here's what's happening. If I take the volume of the entire disk and I subtract out the volume of my smaller disk, which I'll use r of x, little r, that should give me my washer, right? It kind of makes sense. Bigger disk, subtract out the smaller disk, you get a donut, right? So we could simplify this here. Since they have the same coefficient pi and the same integral from a to b, we could actually combine these two. This is really pi integral from a to b of r of x squared minus little r of x squared dx. And here's your next formula, okay? But here's how I want you guys to write it, okay? Just write out and in. That stands for the outside radius and the inside radius, okay? This one takes some practice, but by the end of this lesson, you guys should be somewhat decent with it, okay? Here we go. Let's try it out. Outside and inside depends on the perspective, okay? For instance, like, if I'm standing outside in the sun, I will think that it's hot, okay? But if I'm sitting inside a house where it's air conditioned and I'm looking outside, I probably think it's a little bit cold. So it kind of just depends on where you're coming from, okay? And here, what I'm trying to get at with that poor metaphor is that it depends on where you revolve. Your outside and your inside will be based on where you revolve. So just keep that in mind. Here we go. Here's example 2. Okay. Write this down in its entirety, and then we'll shorthand everything afterwards, okay? All right. First thing you want to do is graph, just like the last one. Here we go. So for red, I'll use y equals the square root of x, which is just the hook. Blue, y equals x squared is just a parabola, which kind of looks like this. And since I'm only looking at the region, which is this right here, this kind of like leaf shape here, I'm going to partially just erase the other stuff because it's really not necessary. Okay? So I'm only going to look at pretty much that region. So I could erase it even more if I wanted to. Okay, so here we go. We will revolve this about the x-axis, so right here. And then since it's a horizontal axis of revolution, okay, I know that my rectangles have to be perpendicular to it. So I'm going to draw a vertical rectangle. Okay, now let me get rid of this highlight so you guys can see. Now, if you think about just that green rectangle, notice how there's a gap right here, right? So I know there's going to be a hole, which is why we're going to have a washer, okay? So you have to know what method you're going to use here. Telltale sign is if they give you 2 functions, most likely you're dealing with a washer. There are some cases where that won't work, but we'll get to that later. But remember, a washer is the same thing as a disc, just hollowed out. So it still has to follow the model of perpendicular, okay? What does that vertical rectangle tell you guys? That tells me that I will integrate with dx. Okay? So I'm going to go from outside squared minus inside squared. I'll actually write it out this time. Okay? Now, for the sake of speeding this up here, the region starts and stops from 0 to 1. We can find that on a calculator or by setting the 2 equations equal to each other to finding out where they intersect, okay? But it does turn out to be 0, 0, and 1, 1. Okay? So I know my bounds are from 0 to 1. Okay, so here's what I mean. This is the challenging part when you first start out. Actually, let me scoot that down a little bit so we have a little bit of space. Okay. We know it's going to be outside squared minus inside squared. This is where you guys have to be really detailed with your drawing, okay? So draw your graphs a little bit larger than usual. Your outside radius will start from your axis of revolution always. My axis of revolution happens to be on the x-axis. So I am going to start here and pay attention to this, okay? I'm going to start here and I'm going to keep going up. And I'm going to stop when I'm about to exit the region. When I'm about to go out of the region, which is right there, that is my outside radius. And then I start somewhere else. When I'm about to enter the region, I stop there. That'll be my inside radius. Okay? Okay, so I know that when I go from the x-axis all the way up here, it hits the red function, which is the square root. So my outside radius is the square root of x. And I know that when I start at the x-axis all the way up and I hit the blue function, that's really just a parabola. So my inside radius is really x squared. Okay? It looks straightforward now, but it does get a little bit technical in a little bit, okay? Here we go. The rest, we're going to use a calculator, Okay, so here we go. Here's what I'm going to ask you guys to do. So we're going to let y1 represent the square root of x, and we're going to let y2 equal x squared. Okay, go ahead and do that on your calculator. So square root of x and y2 will be x squared. Okay, so you're going to go second mode to your home screen, and we're going to try to type this entire thing out. Okay, so here we go. Pi. And then we're going to go to math 9 for integral. We're going to go from 0 to 1. And we're going to go to y1 squared. So that's going to be alpha trace y1 squared minus alpha trace y2 squared with respect to x. So just to double check, just to make sure you guys are on the right track, you should get 0.942 rounded. If you're not getting that, please do text me right away, okay? Okay, we're going to keep going. Okay, and this kind of creates like a bowl shape of some sort. I don't know how you would describe this one here, but again, that's how it would kind of look like there, all right? Okay. Let's, here's part B. Notice how it's the same question, right? But actually what I'm going to do here is I'm going to go ahead and I'm going to say, well, you know what? We're going to rotate this about y equals 50. Okay, so these two functions stay the same. I'm going to try to be consistent here. I think I used red for the first one, so that's our hook. I use our parabola, which is this right here, and we have our shaded region. Awesome color. We're going to rotate this about y equals 50. So remember, y equals is a horizontal line. So I'm just going to say that this is 50 here. And this is where I'm going to rotate. All right. So same thing. We have a horizontal axis of revolution. So my rectangle should be vertical because it's perpendicular. Okay, so I'm going to draw a sample one here, somewhere in the region. That tells me that it's going to be dx. So for the next few examples, you guys, I'm focused more on the setup than I am the answer, okay? So setting it up is really all I'm worried about. Okay, so here we go. I know there's a clear gap here, right? So I know it's going to be a washer, so let me set this up for a washer. And I know the region still starts and stops from 0 to 1. But this is where it gets weird. So pay close attention. Your outer radius starts from your axis of revolution. From. So your axis of revolution is at y equals 50. So we have to start right here at that orange dot. And I'm going to keep going. And right when I'm about to go out or exit the region, I'm going to stop. That is going to be called my outside. Right when I'm about to go in, that will be my inter, right? That will be my inside radius. So I need to figure out what these two orange lengths are. And this is where it gets weird. Okay? So take a look. I know for a fact that when I go from the x-axis all the way up, for instance, if I go from the x-axis all the way up to here, actually, let me draw this somewhere else. If I go from the x-axis all the way up to the blue, that is my y2. Okay, from the x-axis all the way up, that is my y2 function. That's the height. Okay, and I know that if I go from here all the way up to the red function, that's my y1. But the issue is that is not what I'm interested in. I need to figure out what the length of that dotted orange line is. Think about how you guys would get that length. Press play, really think about it. Pause, and then press play when you figured it out, okay? All right, here we go. So here's what we know. We know that from the x-axis all the way up to the axis of revolution, we know for a fact that that's 50. Because when we go from 0 all the way up to the 50 line, that's a length of 50. So using what we learned back in geometry or integrated math 2, if I take 50 and I subtract out that y2, I should get that outside radius. So my outside radius is 50 minus the y2. Okay, same idea. To get the inside radius, I would have to just take 50 minus that y1. Really think about that, you guys, okay? Notice how the y1s and y2s switched in terms of outside and inside because the last one it was backwards. And that's because of perspective. Depending on where you rotate, your outside and your inside changes. And then the answer I don't care about. I'll let you guys figure that out. Really think about the setup, okay? If you understand the setup, move on. If you still have questions, text me right now, okay? Here's part C. I'll speed it up a little bit. Part C, same two equations, but now I'm going to rotate about y equals negative 40. Okay? Try this out on your own. Press play if you need help. So here we go. I will always try to draw a picture. So we have that red hook. We have that blue parabola. Okay? Y equals negative 40 is somewhere down here, a horizontal line. That's where we're going to rotate. Our region is still this leaf-like shape. The axis of revolution is still horizontal, so the rectangle must be perpendicular to that, so it's vertical. So we know it's going to be a dx. We know it's a washer because there's a giant gap. So I'll leave that there, okay? So drawing your outside, you start from the axis of revolution, which is here, and you go all the way up. Right when you enter, that is your inside radius. Right when you go out, that is your outside radius. How do we figure out these lengths, right? Actually, you know what? Let me draw this because that tends to confuse people. Let me scoot this one over here. Because really, you're drawing it everywhere, right? But you want a nice sample one. Okay, so this right here is your inside. Let me scoot this over so we don't get confused. This right there is your outside. Okay. For a fact, you guys know that is an airplane. We know that from the x-axis all the way up to the blue, that is your y2. We know that from the x-axis all the way up to the red, that is your y1. So how in the world are we going to get the orange dotted line lengths, right? Press play if you think you have it. Pause if you want to think about it. I know that from here, just to the x-axis, that's a distance of 40. It would not be negative 40 because distance always has to be positive, okay? So the orange dotted line must be 40 plus whatever y1 is. So that'll be 40 plus the y1. To find the inside, that's really just 40 plus the y2. And some of you guys are probably picking up patterns right now, and that's fine too. I'm more of the logical approach type of guy. And that's it. So notice how in that last one, it was 50 minus, right? This one here is 40 plus. So you kind of have to think about it. And notice how the outside and the inside are very different depending on where you rotate. Okay? Here's part D. D, D. Okay, same two functions, except now we're going to rotate about x equals 60. Okay, x equals 60. All right, we draw our picture. Here we go. We have our hook. We have our parabola. Right? We still have that leaf shape. But x equals 60 is actually a vertical line at 60, so somewhere over here. X equals 60. And that is where we will be revolving this. Okay. Think about what that tells you. Press play when you're ready. So notice here with a vertical axis of revolution, you should have a horizontal rectangle because it has to be perpendicular. Clearly there is a gap, so we know there's going to be a washer involved. So here we go. V equals something with dy. Pi integral of something squared minus something squared. All right? Okay, so we need our outer and our inner length, or radius. So remember, we start from the axis of revolution. So since our axis of revolution is right here, I would have to travel left to get to my region. So right when I'm about to go out, that is my outside radius. Right when I'm about to go into the region, that is my inside radius, okay? Okay, same idea here. I know that from the y-axis, right, from the y-axis to the red function, that is the red function, okay? From the y-axis to the blue function, that's the blue. But remember, everything has to be in terms of y, but we'll get to that, okay? So red, I believe, was y1, and blue, I believe, was y2. I'll use that very loosely, okay? Okay, so the same idea here, right? How do I get that orange length? So use logic to answer this question, okay? How do you get the orange outside length? Press play whenever you're ready, and really do think about this. Okay, to get the outside length, I know that from the y-axis all the way out to 60 has to be 60. But I have to take away that little chunk right there. Okay, so this is really 60, take away that y1 chunk to get my outside orange length, right? So the inside is really just 60 minus y2. But here's the thing. Everything has to be in terms of y. So y1 in terms of y is really x equals y squared. Okay? Y equals x squared, which is our y2, right? So x is really the square root of y. So that's going to go right here, the square root of y. Okay? That means the bounds have to be in terms of y as well. But if you guys remember, the x and y coordinates coincidentally happen to be the same. But I want you guys to remember that we're paying attention to the y coordinates. So that's from 0 to 1. Okay, so when you actually type this out in a calculator, you wouldn't be using the y1 and y2 function because y1 on your calculator is still the square root of x, right? So what I would type in my calculator is v equals pi, math 9 from 0 to 1, 60 minus variable squared, minus 60 minus the square root of variable squared dx. There's a lot of parentheses involved, so you really have to keep track there, okay? If you have trouble with that, just let me know. But remember, my main focus on setting it up, okay? Here's the last one, part E. Well, not the last one, but the last one for this problem. What if I wanted to rotate x equals negative 30. Try this one out here. Draw a picture. Don't try to do this without a picture, okay? I'll draw the first part for you, but you guys can do it here. X equals negative 30 is right over here. It's a vertical line. X equals negative 30, which is where we're rotating about. I want you guys to pause this video now and then try to go as far as you can here. Okay. Vertical axis of revolution means that the rectangle has to be horizontal because it's perpendicular. Okay, so I know it's going to be in terms of y. Notice how I take care of that first, okay? So v equals pi. The region starts from 0 to 1 with the y coordinates. I just need the outside radius and the inside radius. The outside radius starts from your axis of revolution, which is here. And then right where you're about to exit the region, and right where you're about to enter is the inside. Okay, so to get your outside length, that looks like it's really just 30 plus the blue function. So that's really 30 plus the parabola. But in terms of y, if it's y equals x squared, that's x equals the square root of y. Okay, so the inside will be 30 plus the red function in terms of y, which is really x equals y squared. And that's it. Okay, I want you guys to quickly try this one here. New problem, last one for the day. Here's your picture, and draw it 4 different times if you need to, but here are 4 scenarios. You want to rotate this about y equals 60, negative 22, about 5,000, negative 23. And notice how I set up the integral for you, but I did not tell you if it's dx or dy here. So make sure that you include that as well. All right? Okay. So I'm about to go over the answers, so if you're not ready for it, please make sure that you pause. Whenever you're rotating about a horizontal axis, you know that the rectangles will be vertical, so these will be dx's. And these will be dy's if it's a vertical axis of revolution. Since the dx's, okay, the bounds will be from 0 to 1 for the x coordinate. But if you're integrating with y's, it'll be from 0 to 1 with the y coordinates, not necessarily the same, okay? All right, so I'll go in order. If this is about y equals 60, y equals 60 is somewhere up here. That's going to be 60 minus the parabola. That'll be your outside. So 60 minus x squared. The other one will be 60 minus x. Okay? I'll erase so that I can kind of visualize it. If it's y equals negative 22, which is down here, I know that it's going to be 22 plus the functions. So outside will hit the linear, so that'll be 22 plus x. It's 22 positive because 22 cannot be negative. It's a distance, right? So this is going to be 22 plus the x squared because it's touching the inside. If it's, oh gosh, x equals 5,000, you're somewhere over here, 5,000. Okay, so that means you want less, so it's going to be 5,000 minus. The outside will hit the line, so it'll be 5,000 minus y. And it'll be 5,000 minus y equals x squared, or in this case, the square root of y. All right? Okay, part D. Negative 23 is over here. So that means that we want more. So it'll be 23 plus the square root of y, that parabola. And it'll be 23 plus y in this case, okay? Now, if you're looking at these 4, right? If you did not get any of these, or if you didn't get one of these or 2 of these, do text me right away. Yeah, and let me know, all right? Disc and washer. Big takeaway before I end this video, perpendicular. Don't forget that. The axis of revolution has to be perpendicular to the rectangle. The rectangle tells you if you're integrating with x or y, okay? Vertical rectangles are dx, horizontal rectangles are dy. The rest, I hope that you guys can figure out logically rather than memorizing how problems work. Okay? I'm going to stop talking. Okay.